June 2018. The world lost a hero to science and a symbol of the human spirit. Hoppy. Its 15-year-long mission on Mars was brought to an end when its solar panels were covered by dust storms. Fortunately, the latest Mars rovers will have no such issue as they rely on nuclear RTGs instead. The RTGs run nearly indefinitely, dust or shine, on Earth or deep space. But how? Traditional nuclear power is fairly simple, or rather as simple as nuclear physics goes. A neutron collides with uranium-235 to form U-236, which is so unstable that it immediately splits into lighter elements, as well as emitting multiple neutrons, which cause a chain reaction, releasing tremendous amounts of heat energy. Heat boils water, steam turns turbines, turbines generate electricity. But in many situations, there's not enough water nor space for an entire nuclear reactor. Instead, we must use radioisotope thermoelectric generators, or RTGs. And while we're at it, let's use plutonium-238 as our radioactive element instead. Plutonium generates a large amount of heat energy relative to its density, making it ideal for spacecraft where every gram counts. It's stable, easy to refine, and safer. When many radioactive elements decay, they like to give off deadly beta and gamma radiation, which is very harmful to humans and electronics and difficult to contain. Plutonium-238 only releases alpha particles as it transforms to uranium, which can be stopped by as little as a sheet of paper. One downside is plutonium's relatively shorter half-life, although it's still sitting at around 88 years, which is plenty long for most missions. Now, instead of heating water, let's heat semiconductors instead. Multiple thermoelectric generators transform the plutonium's heat energy absorbed by the semiconductors into electricity via the Seebeck effect. Semiconductors aren't quite conductors and often perform more like insulators. For example, silicon and germanium, two semiconductors commonly used in RTGs, have 4 valence electrons and can therefore bond covalently in a tight lattice, restricting the movement of electrons. In their pure forms, these metalloids are considered insulators, although that can be changed by introducing imperfections through a process called doping. One semiconductor, the n-doped one, is given atoms with extra valence electrons. Some are heated, energizing them and causing them to push toward the cooler heat sink to reach an equilibrium. The p-doped semiconductor has been given atoms with more room for valence electrons, called holes, which also diffuse toward the cooler side. Now each semiconductor has different concentrations of electrons on each end, and therefore a different charge, so they may link together to create somewhat of a battery. The downside, of course, is that even fresh RTGs only generate around 110 watts. That's just enough to power a small refrigerator, but scientists are able to make a little go a long way. Perseverance is powered just fine by a 110-watt RTG, which is only around 30 watts less than Opportunity could generate in peak conditions. While solar power provided an initial opportunity for spacecraft, RTGs will truly allow them to persevere further than ever before.